So I have a question for you today. I bet you think about this about 5 or 6 times a day, right? What can we do when trees die of disease on a landscape scale? By the end of this talk, I hope I'll be able to convince you that tree resistance is the answer, okay? Most of you probably don't think that trees can resist anything, but they do. This whole thing started at my young age because I grew up near the southern Alps of my native Italy, and beautiful Dolomites, mountains, beautiful forests, and I enjoyed walking around in the woods, complete with knickers and 80s style glasses, as you can see here. But I soon became more interested in the benefits that trees provide. And I'm sure that most of you, if not all of you, are familiar with the benefits that trees provide. And highlighted here are some that I'll come back to a little later in my talk. So trees are important, and when they die, whether it's a single tree in your front yard or devastation of trees on a huge scale in equatorial forests, for example, in Brazil, these are very important events. And deforestation, in fact, has produced 1/3 of the excess CO2 in the atmosphere since 1750. So whether trees die because they're killed by humans directly through deforestation, or whether they're killed by pathogens, that's where I became interested in understanding what kills trees, and so the pathogens that kill them. But then, soon thereafter, I became very interested in what actually trees do to protect themselves against these pathogens. So I started studying how trees defend themselves, and that's part of my work. So I want to start by giving you a couple of examples of why tree diseases are important. So here you see a map of the United States, and superimposed on this map, there's a plethora of diseases that have destroyed forest ecosystems throughout the last century. Some of them are very iconic, like chestnut blight. Some of you might have heard about that. But I'll be talking about one in particular, which is a mouthful, which is called white pine blister rust, which occurs in the western United States. So the disease kills white pines. And these are trees that are the only ones that can really occupy ecosystems at high elevations in the Rockies. So they're foundational for ecosystem establishment as well as functioning. But they can end up looking like this when this disease ravages them on a wide scale. So you might ask, why is this important? Well, when trees like white pines die on a wide scale, they affect other organisms. For example, red squirrels, which rely on the nuts produced by, or the seeds produced by these white pines. In turn, these squirrels actually store these seeds in large cache amounts in these things called middens. And these middens are actually raided by grizzly bears in the Rocky Mountains. And in fact, the seed from the white pine is a major source of nutrients for these organisms. So if you decrease the number of trees, you indirectly affect grizzly bear populations. So why should you care? Well, when you have trees die in a large landscape scale, all that biomass turns into CO2, which contributes to global warming. So this is through degradation of the wood, for example, as well as perhaps increased intensity and frequency of fires, which, by the way, provide a hazard also for humans. But there are also all sorts of indirect effects. So if you have widespread tree mortality, you can expect an increase in soil erosion and degradation of the soil, effects on water retention and quality, and in nutrient dynamics, which in turn affect the microbial community dynamics in the soil, which in turn affect the amount of carbon that's stored in that soil, which can then turn into CO2 and be released into the atmosphere. But we can also, if you're going to go back to the story about the bears, if you think in terms of the indirect effects of removing bears from the ecosystem, you might think in terms of releasing more herbivores like elk and bison, which in turn will consume more tree seedlings, which is essentially equivalent to say that you have fewer trees. So what can be done? The question is, how do we go from this situation, which is a healthy ecosystem, forest ecosystem, to one that looks like this due to a widespread disease, back to the original ecosystem. So that's a major question in conservation biology, in conservation ecology. Now, due to very strong pressure from both the public and the politicians, or the policymakers, the regulatory agencies are stuck between a rock and a hard place. They need to do something about what is going on whenever this happens. So the typical or traditional approach that is used is something called short-term ecosystem maintenance. So I have a diagram here that shows a forest ecosystem humming along, and all of a sudden at point 2, it's hit by one of these catastrophic events, mortality events caused by pathogens. So you have a loss of benefits from that ecosystem, the ones that we refer to ecosystem services, which is very rapid. You have a lot of trees dying. And if you don't do anything, then in the end, you end up with another forest ecosystem, which may be acceptable or maybe not, but certainly is not a way to go back to the original ecosystem, as I mentioned earlier. The way that agencies try to do this is, by and large, trying to control the pathogen. They try to control the spread of the pathogen once it's established in an environment. And this is done for a very simple reason. And this is a concept that's very basic in plant pathology. It's called the disease triangle, but could be applied to any disease. To have a disease, you need to have a susceptible host, a virulent pathogen, which in forest environments usually is a fungus, and a conducive environment, which for fungi means moisture availability and air currents for spore dispersal. Or you could also think in terms of drought conditions that predispose trees to being infected by these pathogens. Now, as you might imagine, it's basically impossible, if not simply impossible, to control pathogens in forest environments. And you might have guessed it, you can control the environment. So what we're left with is the host that we can play with in terms of trying to control these situations. So I'm going to tell you that host resistance, therefore, is the answer for forest environments. And the proposed approach is one that we call long-term ecosystem transition, and this is one in which tree resistance could really come in very handy. So in the context of this approach, you might imagine that you still have a catastrophic event coming in at point 1, but you try to guide the ecosystem through a gradual change over time so that you're losing trees, but you know where the ecosystem is going, and you're not losing ecosystem services or benefits as rapidly or as abruptly as in the previous situation. And the ultimate goal really is to come back to the initial ecosystem, okay? So to do that, we need to work on resistance. Now, to work on resistance with trees, it's not trivial. So we need tools to be able to rapidly identify resistant trees that we can then propagate or breed for more resistant offspring that we can outplant in the forest environment. So this is where our science comes in. I want to tell you a little bit about Fourier transform infrared spectroscopy, which is a mouthful to simply say that we can generate chemical fingerprints for trees to identify resistant and susceptible individuals. So what infrared spectroscopy is based upon is that all molecules vibrate, okay? Here I have an example of a simple molecule, and these molecules can stretch and bend, and each one of these 4 basic vibration states absorbs a certain wavelength of infrared radiation. And we can use this information to actually create a sum total of all the compounds that are present in an individual and produce a spectrum that looks like this, which includes a fingerprint region. So we can take this fingerprint region and we can apply to different groups of trees, and we can actually identify or separate resistant from susceptible trees. Now, you might see here 3 bands that were identified at 1305, 1735, and 1721. You might say, well, these differences are not that great. But in fact, using powerful statistical data analysis, we can actually separate these trees quite clearly. So we can separate and identify resistant and susceptible trees using this kind of techniques, which is very exciting. Now, These days, we can only do this by taking extracts from the trees and analyzing them through FTIR, or a Fourier transform infrared spectroscopy. But the ideal situation would be one in which we develop a protocol for handheld devices that we could take to individual standing trees in the forest and take a chemical snapshot of the tissues of those trees and being able to say if that tree is resistant or susceptible to that particular pathogen. Now, this technique would be great also for agricultural contexts that include woody plants. For example, the production of cocoa or coffee, which are very important to all of us, I think, but also to many developing economies around the world. So coming back to the real reason that we're studying resistance in trees, which is to be able to act through a long-term ecosystem transition when we're faced with these catastrophic events, I hope I was able to convince you that host resistance is a key. Thank you.